My name is Matthew Miller, and this is Physics 2211 Lab 1. This lab is based on Newton's second law and required us to observe a real-world object moving at a constant velocity. We then used a camera to record the motion and an image tracking software to create a computational model of this motion. Computational modeling is an important part in modern physics, and this was a way to introduce us to this concept and the importance of computer modeling. Comparing the observed motion to the computational motion will reveal how we can predict motion using Newton's second law, assuming a constant velocity. The results showed that there is a correlation between observational analysis and computational analysis. However, it was weak. The first step was to observe an object moving at constant velocity. I observed my friend pushing a stress ball across a flat surface and captured its motion. Using Tracker, I was able to analyze its motion and calculate some values to use in my computational model. I collected data from the ball, such as the ball's diameter, ball's mass, and took note of the start time of my system and end time of my system. I extracted the ball's initial position using Tracker's initial position data, which was the vector 3.637 e to the fourth 00 meters, and that was at 0 seconds. I then needed to calculate an average velocity of the system, so I took the second evaluation point at t2, 0.017 seconds, and used that to calculate the average velocity using the formula v equals change in position over change over time, change in time. I then used GlowScript to input the data to create my computational model. The ball's mass, the ball's position vector, and the ball's average velocity vector were all used to set up the physics of my model. I then needed to change the fnet vector to 0, 0, 0 to achieve the constant velocity. The ball's velocity and the ball's position formula were also adjusted to be in line with constant velocity. The model data is represented on the left with a constant velocity, and the graph and data from the tracker simulation is on the right. I then extracted the data from both of these programs to compare both lines in one graph. Using Google Sheets, I compiled this data into an observed and modeled comparison chart. The lines don't match perfectly. The modeled is represented of a system with perfect constant velocity, and the observed shows the ball gradually slowing down due to the friction of the table. We conclude that there were net forces acting on the ball causing it not to have a perfect constant velocity. What if the axis of orientation had been flipped? In my simulation, I chose to orient my system so that the ball moved in the negative x direction. We could have chosen any of the directions, positive x, positive or negative y, or even positive negative z direction, and that would be the only change in the system, the direction vector. However, the relationship between the object's velocity or position relative to time would be the same. Is it possible for you to say how many pushes and pulls are added together to get a zero net force in the case that you observed? In the case of the ball rolling across the smooth surface, the force of the hand pushes in one direction, and then the table's friction pushes in the opposite x direction. In a perfect system, those would cancel to give you a zero net force. The force of gravity and the force of table will always cancel, giving you a vector of 0. And assuming that the ball is moving in a straight line in the x and y coordinates, the z vector would also be 0. Thank you.